Hi everybody, I just want to give you this short lecture on capillary rise. It's something we all saw in the field at Hazelrig, where our pits were flooded at the bottom of them, and we saw that kind of damp zone towards the bottom of those pits. So I just want to talk a little bit about the soil physics that are going on in the soil that's controlling that. So let's just think about some of the fundamentals, and there's actually a really good section on this which goes into more detail than I'm going to go into in this mini lecture in Brady and Weil, page 176 in the online version. There are two principal forces at work here that are drawing water from the water table up into the soil, and together we call that capillarity. The attraction of water for the solid is called adhesion. So you can imagine that you have a solid which is hydrophilic, i.e. water loving, and the water is going to be dropped onto that solid. Perhaps it's a glass surface, and the water spreads out over the solid. We then have the cohesion between water molecules. So this is what would hold the water together on a surface that is repelling water, hydrophobic. So some of you might have a Gore-Tex jacket for going out in the rain, and you'll see water beading on the soils, on the jacket surface, and that's due to cohesion. If we think about this in a soil context, it's easiest to think about it in terms of a tube, and you can imagine the soil as a series of lots of tubes of different sizes representing the different size pores. And where we have adhesion that is greater than cohesion, so the attraction of the water molecules for the sides of the tube, in this case you could imagine it as a glass tube, and where that is greater than cohesion, the water is pulled up inside the tube. The smaller the tube bore, the higher the water rises. And there's a very simple equation that we can use to describe that with water at 20 degrees, which is the height of the capillary rise is equal to 0.15 over the radius of the tube. And I've got a picture here taken of some tubes of different sizes which are drawing coloured water up into them, and you can see very clearly that the smallest diameter tube has the highest rise, largest one the smallest rise. So if we look at that in the context of Hazelrig, here's one of our pits. Up in the higher parts of the soil profile we have an unsaturated horizon, and just close to the water surface there we have a saturated horizon, and that saturated area has all the pores filled. And obviously what's going to happen is that water is going to be drawn up by capillary rise into this zone, and that zone will become close to saturation as water is drawn up into those pores by capillary rise. And you can see that a little bit more clearly in this picture that I've pinched off the internet. There's the web address there, and you can actually see the damp zone where water is being drawn up into this soil profile quite clearly. The height of that capillary rise depends on the soil type. already seen that smaller pores or smaller tubes draw water up to greater heights, and the same is true of soil. So if you have a fine textured soil such as ours at Hazelrig, you're going to get a higher capillary rise than you will if you've got a sand. It'll be faster initially in the sand because the pores are bigger. Okay, so the water can move much more freely through them, the hydraulic conductivity is greater, but over time the finer textured clay loam soil is going to overtake both the sand and the loamy soil. So thanks for watching this short video. I hope it's explained some of the phenomenon that we saw in the field, yeah, thanks for watching.